Hello everyone, I would like to present a new feature of mwemu that allows to capture a specific moment and transfer it to Radar 2 for further analysis. This is Radar Congress 2025. I'm gonna explain a bit about the project and then some details about Windows process internals. Because while you're emulating a binary, there is a process address space that is changing, and you can capture a specific moment and interact and understand what is going on. So for this talk, I'm gonna use a sample packet with Enigma. In this case, the purpose is not doing full emulation of the unpack. Is showing a concept of doing reversing static and emulation at the same time, and then I will explain how I did integration with Radar 2 and some examples and a demo. Okay, this project started in 2021, and the purpose was controlling algorithms and predicting things in general. So imagine that we have a kind of magic crystal ball that can predict the future, and you have a malware, and you can make questions to that prediction system. And then you ask, for example, this malware, when I execute this malware, where is gonna connect? Where is connecting this malware? But I don't want to execute the malware because it's unsafe. So the emulation is without executing things, know what will happen, because the malware thinks that it's being executed but really is being emulated in a safe environment. For doing this, I need to do a hardware emulation and operative system simulation together. The hardware supported is x86 and is focused for Windows mainly. There is some basic support for Linux. libc can be emulated, for example, but not the linker. But the 32 bits and 64 bits are implemented in a same engine. This was implemented from scratch, except for the conversion from bytes to assembly objects. That I said x86, that is also Rust. So this is a pure Rust implementation, and it's open source. Initially, the name was sha0coder, like sha0coder, but I have to change the name to mwemu because I realized that sha0 in Italy, I think, is a bad word. The hardware emulation is quite reliable. There are no problems. It's very weird. It's uncommon, the situation where it found an unimplemented instruction. Despite I only implemented 364 instructions, and the processor can have much more instructions. But all the compilers are using same instruction, and I'm also implementing exotic instructions like XMM and YMM. That libc is plenty of YMM instructions and can be emulated. And there is the flags and the registers. The flags are quite stable. The floating point unit is a basic implementation, but supports the float 80 bits. Note that Rust supports maximum 64 bits of floats. But in some operation, I'm losing some bits because otherwise I would have to do tailored polynomials and this stuff. When the assembly instructions jump to the operating system, this is detected and triggers the simulation. Well, the simulation, there are several file formats. There's a kind of loader, can load a PE. There is the delay loading, the IET binding. Well, there are several processes for loading and creating. It's a simulation of a process. It's not all the Windows simulation. It's like a process. We have an address space. We have some structures and so on. There are 615 Win API implemented that really are not much because there are many more in Windows. There are, yeah, the hardware is quite reliable, but the OS simulation can have to, emulating a malware. You can find that error, the Win API not implemented, for example. But I try to fix the stack and follow the emulation. I implemented exceptions, Linux iscals, and several allocators. There are 3 ways to use mwemu. Can be used from command line. This talk is mostly about command line, but can be used from Python. When I worked in malware analysis, I used a lot the Python module because you can pinpoint more and configure more the emulation. And also, it's possible to do Rust applications using the Crate, the Rust library. So the Rust library and the Python library are public. And this can be used for Linux, Windows, and Mac, but is focused for Windows binaries. Well, I was very lucky because this project liked to do some reversers, and they want to collaborate with the project. They also love Rust, and they well increase the quality of the project a lot. Some details about the how is a process from inside, and well, when you run a calculator, for example, there are several dependencies that are loaded in loading time. Other dependencies could be loaded like the loading or things like load library A. So when the program needs the DLL loads it, but most of the DLLs dependencies and dependencies of the dependencies are loaded at loading time. There are several structures in the memory. We have to simulate a real process because the malware is going to access to structures, is going to crawl some linked list and so on. It could be several stacks, several heaps. The malware could unpack or decrypt some PIC code or some shell code. Or directly, instead of analyzing a DLL or a exe, analyzing a shell code directly. Also is possible. Well, every module DLLs and exes. Not all the file is loaded to the memory. Specific regions, specific sections like code, data, and data read-only initialized. And the header is also loaded to the memory. There are 3 main structures that are the tab for every thread, some metadata of the thread, some metadata of the process, the web, and LDR is a kind of triple linked list pointing to different offsets for the first entry, and then it's like a circular list that is triple pointed and is forward and backward. There are the fling and the blink pointers to walk. Really, there are not only the DLLs, there are also the exe is also linked in this list. Well, it's possible to capture a specific moment in the emulator and check the memory, and there are some commands. This command line of this console of the emulator is quite basic, cannot be compared with Radare, but I implemented a radar2 command to trigger Radare and inspect this using Radare. There are nice commands like LDR to visualize the linked list. And let's do an example with an Enigma packer. Okay, this is using mwemu from command line. Then this is the sample, and let's simulate 64 bits the first 1 million instructions in verbose mode. What we found is that this packer at the beginning what does is a short loop, a typical short loop, but this short loop really are this amount of instructions. This amount of million of instructions, probably for anti-emulation or for protecting the next stage, but for malware this is not an anti-emulation because it can be emulated in just 11 seconds and something. And well, every program in a specific moment does the first epic call, and in this case is this. I removed the verbose mode because this speed, for reaching the maximum speed, you need to remove the verbose mode, which is a bit more slower. And even when I don't put the verbose mode, I'm capturing this moment when it emulated this amount of instructions. Previous instructions, automatically the verbose is enabled and the trace also is enabled. And we can see that it's going to call this API. Okay. Let's do a full emulation try at least. I don't specify any moment, so it's going to emulate everything. I could also log to disk, and we see only with no verbose, we only see the API calls. And in some moment, in a specific moment, crashes. So the operative system is a simulation. It's not a real operating system. Sooner or later, the malware would crash in a full emulation mode. But well, in this case, we can dump to this the state, or we can do several things, or inspect that moment what is going on. Or in this case, it's not implemented this, and implemented it, and so on. Well, there are malwares that can be fully emulated, but normally you have to prepare the emulation of a specific function with mwemu. Okay, let's see the radar to integration. It's quite useful, for example, for visualizing data blobs. So if I capture a specific moment, in this moment is calling this API, and this library uses this type of object, the bstr object, which is a string. This string object is probably not very intuitive because the pointer doesn't start in the first byte. It starts in the string. It's a white string, so one char is 2 bytes. This is a white null char terminator, which are 2 bytes. And then there is the length in bytes, not in chars, and not including the terminator. In the offset -4 is the word of the length. Okay, let's display this with radare, for example. In that moment, I use the command radare to this address. In that moment, this is spawn radare, and this is not a simulation, this is the real radare. And well, the API shows some information. We know the buffer address, and let's inspect that address. Radar is synced with this memory map. The registers are transferred. The seek, so the offset is transferred, and so on. So we can see that this pointer is directly to the string itself, the white string. But if we do -4, we see the size of the string. If we can convert it in decimal, and this is amount of bytes that match with this. And well, it's all the power of radare inside an emulation moment. But well, here we are using an address that is a buffer, a blob, a memory blob with data. But we can use a code address also, and doing the A's for analyzing the map. And well, in this case, PDF to check where the function starts, PDC to decompile in a pseudo-C that doesn't lose information about the registers and so on. So it's a nice way of viewing the functions. I try to find cross references, but in this case there are no cross references. Probably Enigma is obfuscating them, or for any reason there is no cross reference to this. But well, we have the emulation trace, so we can know who called this function. So it's a complement. There are things that only can be known in a dynamic analysis. You know, the static analysis is the way, because you see all the paths at the same time. When you execute the malware goes in one path, not in all the paths at the same time. But there are things that are not known in static analysis and are known in dynamic analysis. So this has the advantage of static and dynamic, but without running the malware. You can use even the AI. In this case, well, it's a case where it's just a function that does a call to the API. But you know, it's just an example. You can use all the power of Radare inside the emulator. So how it's integrated? Well, I have to improve this because for now I'm using files. I'm dumping the memory to a specific map. So you want to use Radare to this address. I locate in which memory map is this, and I save the map to disk, and load Radare to this file, and then remove the file. It's not I have to improve this. I have to use memory pipes or other type of I/O. In this case, I'm transferring the register values. So in Radare, I can use the registers. Well, I'm configuring specific AI models, and I'm transferring the architecture, the base. This is quite convenient because when you use several reversing tools at the same time, it's quite convenient to synchronize the base address. The seek also to have this pointing directly to this address. And the Rust magic happens because this is a fork and exec, transferring the std in, std out, std. So transferring all the user interaction to the Radare. But if in Radare, for example, I press kit, returns to emulation and I can switch between both contexts. Okay, let's do a demo. Well, this is a test, automatic tests that when you deploy or do a pull request to the JIT, is ensure that there are no regressions and so on. Some of tests are artificial tests of specific functions, and there are also checking shell codes, patched shell codes and binaries. And well, in this case, I'm going to use the command line. And I know that if I launch this without specifying any moment, it's going to arrive to this moment and then crash. But in this case, it's arriving farther than the debugger, so it could be interesting to check where what is going on in this moment exactly. So this is going to take some time. It's loading. Well, it loaded prepared the virtual process, loading and linking the DLLs. You can customize the base address. In this case, was the auto-detected. Get procats to get the addresses, and so on, heaps. And there are heavy loops that will take time. For example, now we are in the first 200 millions of instructions were fast, but then takes some time. Yeah, a friend optimized the logger. Is using buffered logger because every print, every line of log is it would be a syscall, write syscall. So in buffered mode, the problem is the order could be not real, but in this case, there's no problem. And it's faster than doing the unbuffered. Well, now it's in the 600 millions. It is near to the crash. And before crashing, this is not correct because if we press enter, if we press enter, this is going to be emulated and call the API that make the crash. So in this case, let's inspect what is going on. We can check the memory and other stuff. But what I'm going to do is to, for example, check this code address. And well, I have configured the radar HURC to configure in this way. You know, this is a packer, and this is not this memory map is not a PE, so it's expected this. Radar is going to detect all the functions in this memory blob. Anyway, we can check the cross references and so on because are detected in static time, but we combine static with dynamic, so we can know exactly who called these functions. This called this. And we actually there is a call flag for tracing all the calls that could be useful. And well, here we are. This detect many functions in this memory blob. And well, actually, there is no emulator that can detect functions, for example, do a static analysis, because in this case, it's rather doing the static analysis. And well, with this display I have configured, I can see the current pointer or offset and where the function starts. In this case, it match, and I can do this and check the cross references in static. But how to know which caller called this function? But in this case, there's no problem because we have the dynamic analysis. So the previous call was done from this address. So see this address. This address is not the first instruction of the address of the function. Is this offset? So we can, for example, we can look at this. This is a kind of the compilation. See, sha0coder. In the compilation, there is always loss of information. So in this case, it's more convenient because you don't lose the information about the registers, and this we can do AI to decompile in Python, for example. Okay, I like the XT, but there is XG, I think. Yes, I like a lot this feature to see traces, because here we know exactly the color, but we don't know all the possible colors. So in static, we see all the paths. So we combine the information we have only in dynamic with the information that they can only know in static. So it's a quite convenient way. Well, in this case, the visual mode works perfectly, and we can use all the views. We can, for example, we can return to the emulator, return again to the radar. Okay, okay, we return to the emulator. For now, we are syncing only this map to Radare, but one option is linking at the same time all the maps. I'm not sure if it's a more convenient way. The current way is quite good, I think, but other option is linking everything, like a kind of sharing memory in some way, but it has to be in a safe way. Saving to file and opening Radare to a file is an option, is the current option. So we can see there is a lot of buffers, a lot of allocations, especially these allocations, virtual allocs and so on, and also the BSTR allocations. Probably because, if the malware or the program does a memory free, for now the monitor is not free in any allocated space, because to preserve the data. One option is, for being more realistic, to if the malware or the software do a memory free the map, but first doing saving it in a disk. For example, one thing we can do is like memory down to disk, all the locations, like I don't remember now the name. I think it is. Yeah, okay. Yeah, okay. And we can check with Radare directly specific allocations or from here also. So I'll do it like this. Other thing, how can do this? Well, there are nice commands like the entropy mode and there are things to trace strings, trace registers, specific register or all the registers, log to disk. Well, there you can put expressions in this way to monitor specific memory regions, call trace, string trace, and so on. This also the entropy. Let's try this. And we can detect, obviously this is a slow way to do the emulation, it's very slow. But note that we don't have a lot of control from command line, but from a Rust application or a Python application we can customize and everything more. So we can enable the entropy in a specific moment and so on. This entropy variations is good to see how is unpacking the unpacking progress of the maps, or which map, for example. Yeah, 7 and something could be code simply. A good encryption is 8 or more. Data could be 3, 4, and so on. No, so we can check which maps are encrypted and so on. There are cool features. For example, pre-program a command like in a specific moment. In this moment, for example, this launch a set of commands. For example, this is capture the first instruction. Let's put verbose. And with enter I can do emulation like this. This is the initial loop. This one is something. And well, we can do search and a lot of stuff, stack and well, what else? I'm remaking the exceptions. Let's see. Exceptions. No, it's not this. This is the whole implementation, I think. This. This is not done yet because it's a bit tricky, because there is a kind of exception hierarchy, like first the vector is the exception handlers, the chain of the sec chain. The sec chain is different in 32 bits than in 64 bits. Then the UEF and so on, and every exception can return a different code. And the logic is different for every code, and well, I know there are malwares that glue there that use context recovery tricks to hide the obfuscation flow. So and actually was working this, but I am doing a lot of refactors, and probably now it's not doing well the exception recoveries and this stuff. Well, I don't know what else to show, but this documentation, I put a grep because to locate things in the code, and well, we are doing several new features. Let's do a use case. for instance, let's capture the moment where there is the short loop. Okay, the short loop is the showing something in the register, and the register points to this map, which is in this map name. Okay, let's see one thing first. Okay, let's do, so it's shorting, and the moment pointed at this register is well, what's it here? This is shorted, and the previous iterations, you see, there is a kind of different pattern. This is shorted and unshorted. So it's unshorting. We can use the entropy view. It's clearly different pattern. So this here a kind of shorted, but you know the short is not very safe and makes some patterns also. But it's clearly well, we know the algorithm is unshorting. So let's point to some unshorted thing to see what is unshorting. Is this code? Yeah, this could be code. Well, but there are this could be code, or is a yeah. If we try to disassembly, there are invalid instructions. There are something that probably don't make. This could be casualty. Well, I don't. Yes. Yeah, I'm not sure if this is code. I already did this. No. Okay. To see if it's code or not, well, in first place, the function is recognized, but it's recognizing casually in same address. So probably there is there are functions, few functions, could be random, could be really not code. One option we can do is PDC. Or PDG. We are in yeah. So don't seem to be code really. Well, this is below, so it's not. This is after, so this should be the shorted. Are invalid instructions, so it's not code. This is not code. Let's continue a bit more to the shorting. I could do breakpoints. For instance, I don't remember how. Break on a specific instruction. Instruction, I mean the moment, like this, for example. Continue. And now it's here. Aye. Okay. Does this make sense? Well, I want to check loops, because in the loops you can see if it makes sense or not. Well, you know, in Radar you can do cool features like PDG. I'm not sure it's something like this. This column and decompile massively. And what we see in 1 while 2, this makes sense because it starts in this number and is subtracting 1, which makes sense, and check the if arrays to 0. So it's a backward loop, makes sense, and also this loop is showing the content, the pointed the reference, and modifying the pointer, and showing probably this is the showing algorithm we are there. No. This is this map is not the code map. Well, you know, this is a matter of time. So for now, let's keep this here, and you know, this. I hope this could be helpful. So, yeah, thank you. If you have questions, probably there is a chat where I can answer this. See you.